Hello everyone, my name is Ximing Wu. The topic of my presentation today is performance of geosynthetic reinforced soil walls with marginal backfill subjected to rainfall. First of all, let me briefly introduce myself. I'm a PhD candidate of civil engineering in National Taiwan University. Besides, I'm a professional soil and water conservation engineer. And I would like to thank all the professors, partners, scholarship of Technical Foundation, and the Ministry of Science and Technical Program for the successful completion of the research. The presentation can be mainly divided into 4 parts, namely introduction, model test, results and comparison, and conclusion. Introduction. First, introduce the definition of geosynthetic reinforced soil wall. It is the structure constructed by the compacted soil and geosynthetic, which is stabilized through the interaction. It mainly consists of facing, backfill, reinforcement, and a drainage system. Generally, if the inclination angle of the wall is greater than 70 degrees, it is called just wall. If it is less than 70 degrees, it is called just slope. In this study, we mainly discusses the design of the just wall. GIS structures are widely used all over the world, mainly in slope stability and river embankment protection. The advantages of the GIS structure mainly include high allowable settlement, short construction period, good earthquake resistance, and good ecological function. As shown in the right figure, some criteria set the requirements on the backfill's particle size distribution. It can be called marginal soil if it does not meet the criteria, which has the disadvantages of low permeability and easy accumulation of water pressure. However, due to some restrictions or considerations, marginal soil is still often used, including economical consideration, environmental consideration, and the local regulation. Based on the above motivation, the objectives are as follows. First, investigate the final mechanism of the GIS wall subjected to heavy rainfall. Second, investigate the improvement effect of the reducing vertical reinforcement spacing. And third, propose the design method of the GIS wall with the marginal backfill subjected to rainfall. Model 10. The soil used in the research can be divided into 2 types. First is the marginal soil, used as backfill, which friction angle is 35 degrees. The other is the sand, used as a filter, which friction angle is 37 degrees. There are 2 main types of reinforcement parameters, namely reinforcement properties and the soil reinforcement interface properties. The model similarity reverses Bourguignon-Pie theorem to reduce the model, and the scaling factor is 5. Many reduce the geometry, soil parameters, reinforcement parameters, and the rainfall-related parameters. The model configuration of this experiment consists of 3 parts. The rainfall system provides a stable rainfall of 75 mm per hour until the end of the test on the model is collapsed. The monitoring instrument consists of 2 pool water pressure transducer in the water tank and 6 volumetric water content gauge in the reinforcement zone and the retention zone. And the size of the model is 77 cm in length, 30 cm in width, and 60 cm in height. In this research, there are 4 sets of experiments, which is changing the vertical spacing of the reinforcement. As shown in the table, half of the groups are collapsed, but the safety factor is all greater than 1, It is hard to determine whether failure will occur by the internal stability, thus, the failure mechanism needs to be further investigated. In this study, the relationship between the rainfall intensity and the duration was determined according to the Horner formula. The rainfall intensity is 75 mm per hour while in the Taipei area. With 100-year interval recurrence, the rainfall duration is 225 minutes. With 200 years interval recurrence, the rainfall duration is 300 minutes. With extreme rainfall events, the rainfall duration is 425 minutes. Results and comparison. Take the PIV image analysis results of SM15 as an example. Introducing the failure process and shear strength distribution. Let's see a time-lapse video of the experiment. It is collapsed at 75 minutes, which is the top layer failure. At 55 minutes, tension crack began to develop. The failure mechanism is that rainfall infiltration leads the metric suction decrease and the effective stress drop, resulting in deformation on the wall. The shear strength distribution is along the failure surface, and the failure mode is stereoactive failure. At 65 minutes, pull-out failure occurred. The failure mechanism is that the continuous infiltration causes the failure surface development, which cannot penetrate the reinforcement and then develop backward. The shear strength distribution is concentrated on the top of the wall, and the failure mode is local pull-out failure. At 75 minutes for collapse, the failure mechanism is that the wall top layer collapses because the failure surface developed beyond the end of the reinforcement. And the shear strength distribution is concentrated on the top of the wall. The failure mode is the top layer failure. This is the final wall deformation. You can be seen that SM20 and SM15 collapse, and larger spacing creates large amount of deformation. This is a comparison of wall deformation. As shown in the figure, when spacing is smaller, the GIS wall can withstand more extreme rainfall events, in which SM10 does not even have any deformation. This represents that reducing the spacing of the reinforcement can delay the existing deformation occurrence. This is the pore water pressure distribution. It can be seen that the water pressure of different groups began to accumulate at similar time, and the maximum water pressure accumulation is about 18%. This is the safety factor versus wall deformation. Based on the two-premise hypothesis, the results show that if we want to keep the GIS wall under safety conditions, the safety factor should be larger than 2 under 100-year recurrence interval. The safety factor should be larger than 2.3 under 200-year recurrence interval. And the safety factor should be larger than 2.6 under extreme rainfall events. This is because the failure surface is blocked by the reinforcement and will extend backward, causing failure and resulting in an overestimate of the safety factor. Conclusions. First, design with traditional safety factor without additional considerations, GIS wall may failure subject to heavy rainfall. Second, reducing the reinforcement spacing can reduce the amount of deformation and increase wall stability. And third, under proper design conditions, the marginal cell can still use as backfill for GIS wall. This is the end of my presentation. Thanks for your great attention.